Welcome to comp452 computer architecture, and this is lecture 7a. In this lecture we will be talking about exceptions in MIPS processor, and the first thing that we need to answer is, what are exceptions? Exceptions. Basically, exceptions are events other than branch instructions and jump instructions which change or alter the normal sequence of instructions. For example, let's suppose that you are doing for example, you're doing an addition operation. You add two positive numbers and the answer turns out to be negative, or answer comes negative. So this is an arithmetic overflow, and this is an example of exception. Adding two signed numbers and getting negative two positive signed numbers, adding two positive signed numbers and getting negative answer. This is example of an arithmetic overflow. Arithmetic overflow. And I'm sure you remember we talked about this in Appendix B when we designed our 32-bit ALU. So this is an exception. Okay, then there's another possible exception. For example, processor cannot decode the opcode. We call it bad instruction, or we call it undefined instruction. So this is also an example of exception. Okay, let me give you another example. So this was first, this was second. There's another example. You access memory illegally. So this is an example of exception. You may have seen it in operating systems. When you dereference a null pointer, that causes an exception. So these are the events which take place inside the processor, and they alter the normal flow of sequence of instructions. So these are called exceptions. So later on, this framework was also enhanced or extended for I/O devices like hard disks, scanners, mice, keyboards, and other hardware devices, IO devices, to connect or talk to the processor or communicate with the processor. Now we have to keep in mind that there are other examples of exceptions that we will cover in chapter 5. Let me just give you a hint. TLB miss we'll talk about in chapter 5. Then there is a page fault, again chapter 5. So you may have actually studied both these in OS course, operating systems course. Now let me tell you, Intel doesn't use the word exception. Intel calls everything interrupt. For Intel, everything is interrupt. Okay, but MIPS convention is, if you follow the MIPS convention, then we will use the term exception to refer to alteration in flow control, primarily due to some internal event. And if it's an external event, for example IO device trying to communicate with the processor, or for example network Ethernet device or Wi-Fi device trying to contact with the processor, then we will call it interrupt. Okay, so this is the MIPS convention. And in chapter 5 we will talk about page fault and TLB. TLB actually stands for translation loci buffer. This is used to speed up virtual to physical translation, virtual address to physical address translation. And I'm pretty sure you know about this. You studied this in your operating systems course. So our pipelined architecture right now, as of now, it has to support two types of exceptions. We must support, let's call a arithmetic overflow, and B, undefined instruction. And other exceptions, we will not talk about them until we get to chapter 5, which will be after this topic is completed. Now, what is the first thing, what is the most important thing? Actually, all of the things that we have to do to implement exceptions, they're important, but the first thing that we want to save is the address of instruction causing exception. We want to save it. Why do we want to save it? Because after saving this address, we want to transfer the control to operating system, and we transfer control at some predefined or pre-specified address. And from operating system course you will also know that the mode of the processor also changes from user to kernel. If it's a general purpose processor, for example like Intel Core i7 or any of the Intel processors or any of the MIPS R3000 R10000, these cores, any processor that supports virtual memory, physical, and it also supports this change of mode. This is actually slightly loose statement, but generally in a general purpose operating system, in a general purpose multi-user multitasking operating system, when control is transferred to the operating system, the mode of the processor changes from user to kernel mode, and in kernel mode processor can execute all the instructions that are there in the instruction set architecture, whereas in user mode it can only execute a subset of instructions. So but all of this belongs to the OS course and you have already studied that. Now after the control is transferred to the operating system will take OS takes control. Actually let me operating system takes control, OS takes control, and when OS takes control at a specific address, it does whatever it needs to do. It does whatever it needs to do, and then it sometimes or often most of the time it kills the program that caused exception. For example, in case of bad instruction and in case of this illegal memory access, definitely the operating system is going to kill the process which caused that exception. But this is not always the case. Now when if operating system, once the operating system takes control, it needs to know what it needs to know the cause of exception. It needs to know the cause of exception. It gets the address, OS gets the address, OS gets the address of the instruction causing exception, but it also needs to know what was the exception, what was the type of that exception. So we have in MIPS we have a cause register. This cause register contains a code that tells OS the reason of exception. This is one method. The other method to tell the reason of exception is vectored interrupt. Vectored interrupts. Now vectored interrupts, this is Intel pioneered it, and all x86 processors, at least when they were working in real mode, actually also in protected mode, they had vectored interrupts. Vectored interrupt means that each type of interrupt or each type of exception causes the operating system or causes the microprocessor to jump to a specific address and start executing instructions. That's vector. This is what we call vectored interrupts. So in x86 processor, the original 8086 processor, the first 1024 bytes in the original x86 processor were used to store addresses of 256 possible subroutines or interrupt service routines, ISRs. So in original x86 processors, the interrupts were numbered from 00 hex to FF hex, which is 256 interrupts. So each of the address was 4 bytes. First 2 bytes were segment address, and the other 2 bytes were segment address and offset address. But let's not talk about that, because we are not interested in Intel processors. So we will not be implementing vectored exceptions or vectored interrupts. We will focus on the MIPS convention, in which whenever exception occurs, we jump to a specific address and starts executing code from there, and that is the address where operating system gets control and determines the cause of exception by looking at the cause registers. Now we can actually implement all this easily. It's not difficult. So what do we need? What do we need? Number one, what do we need? What do we need? One, a register to save address of instruction causing exception. Okay, now in MIPS it is called exception program counter, EPC. So just like other registers, it is a 32-bit wide register, and this is needed even when the interrupts are vectored or exceptions are vectored. Number two, we need a register to record cause of exception. So we call this cause register. If you guys start your Mars simulator, I think in comp452 you will find this cause register. It's there. Okay. So in our case, we only want to we are assuming that there is a 5-bit field, and that 5-bit field is used to encode various reasons of exceptions or various causes of exceptions, and we will be implementing only 2, and we will use 10 for undefined instruction, This will be a 5-bit number, so it means 01010, 5-bit number 10. Undefined instruction, and then we will use 12, 01100 for arithmetic overflow. Arithmetic overflow. These are the only two things that we are interested in. Okay. All right. So now what we want to do is we want to talk about what type of signals do we need. What type of signals do we need? Additional signals, control signals. In order to determine how many additional signals we need, we must talk about where the exceptions can take place. Where the exceptions can take place in our pipelined data path. So let's see. This is let's say this is our instruction fetch stage, this is our instruction decode stage, this is our execution stage, this is our mem stage, and this is our write back stage. Now arithmetic overflow will be detected in execution stage. This is where arithmetic overflow is detected. Okay, and undefined instruction is detected here in ID stage, because this is where we look at the opcode. So this is undefined instruction is detected here in ID stage, instruction decode stage. All right. Now what do we want to do when we detect these exceptions? What do we want to do? That's the important point. First thing that we want to do is that we want to let's first talk about arithmetic overflow. We have detected arithmetic overflow in EX stage. What do we want to do? We treat these exceptions as a type of control hazard, and therefore when we detect arithmetic overflow exception in the EX stage, we want to first of all stop further processing of the instruction in EX stage. Let's talk about arithmetic overflow. When detected, we want to stop the instruction in EX stage. Now for this we will need control signal. We will need control signal to do this. Okay, we want to do one more thing. We want to stop the instruction. This was the first thing. Let's use a different color. Let's say that this is the first thing that we want to do, and the second thing that we want to do is stop instruction in ID stage, because now we want to go to a totally different address. So the ID stage instruction must be uh, stopped, or it must be converted into a no op. This is what we want to do. So we will need a control signal. This looks more like a 9, and that's why I don't like it. So let's try to make it, we will need a control signal. Okay, all right. So what next? Third, what is the third thing that we want to do? Number 3, we want to stop instruction in fetch stage. Now this is very interesting. We already have a signal and we called it if.flush. We already have this signal, if flush. And the last thing that we want to do is we want to load a special address in program counter register. And in case of MIPS, this is usually the address 0hex 8000 0180. Now it's your job to figure out. Look at page 42 of the MIPS assembly language book, and then there's a colored diagram. It colors different memory regions using different colors, and it tells you what is the range of each memory region. So it's your job to figure out where this address lies, in which memory region this address lies. So you have to figure it out. You have to find it out yourself. Okay. All right. So these are the 4 things that we need to do. Okay. Now, why do we want to stop this arithmetic? Why do we want to stop this instruction in EX stage? Now, this is something important. So let's discuss it. Suppose that the instruction that caused arithmetic overflow exception was this. This is the instruction. Now, if we do not, and you know that the overflow was detected in EX stage. If we do not stop this instruction in EX stage, what's going to happen is that the value of the register 10 or the contents of the register 10 are going to be overwritten in the write back stage, and we will not be able to see or examine the value which caused exception. So that's why we want to stop the execution of this instruction in EX stage. We want to stop the execution of instruction in EX stage. Okay. All right. So now what we are going to do is that we are going to name the signals, and the signal in the EX stage we will call it, let's call it EX flush, and the signal in the ID stage, let's call it ID flush, and we already have IF flush, already have it, okay. And we will also need to extend the multiplexer, which loads value in the program counter register. Extend mux that loads values in PC, and everything will become clear when we have the figure in front of us. Everything will become clear. Okay, so this is the introduction to what we are going to be doing in the next part of this lecture 7b, and I think we will wind up our total discussion in lecture 7b, knowing that we will have to revisit exceptions in chapter 5. We will have to revisit exceptions in chapter 5. So I'm going to stop at this point, and in the next part of the lecture we will have the data paths in front of us with control signals also shown on it, and then we will see that how we are going to use these two new signals, and how we are going to change the mux, how we are going to extend the mux that loads value in the program counter register. And all of these new signals, they will come out of the main controller. They'll come out of the main controller. But you know that arithmetic overflow exception is detected by the ALU. Arithmetic overflow exception is detected by the ALU, and undefined instruction is detected by the main controller itself, because it examines or it receives the opcode of the instruction. So let's stop here, and we will begin our discussion. We will continue our discussion in lecture 7b, and hopefully complete it as well. So I'm going to stop, and there we go.